In this video, we're going to be looking at two related topics. Doubling time. Let me start with this one. This is the amount of time. Oops, I didn't want that to come up. The amount of time required for an increasing quantity to double in size. So let's look at doubling. This isn't going to be a very long video. I'm basically going to show you how to use a calculator or a computer to solve these problems, but the problems themselves will provide some insight, depending on whether the item that you're studying is increasing or decreasing. Right now we're looking at increasing. So as an example, suppose an investment is increasing in value by 10% per year. What is the doubling time? Basically, I want to look at, let's say I've invested $1. So that was my start. Now, if it's increasing by 10% per year, that means after 1 year, I have $1.10. And then after 2 years, we're going to take the previous one. Here's how you make it. Here's how you get it to work. You do 1 plus 0.10. That way, you not only take the amount you had in before, you also put in 10% more all in one shot. So when I do it, I'll do 1.1 and then times, start a parenthesis, and go 1 plus 0.10, end the parenthesis, and hit enter, and I get 1.21. And this goes on. I would like to know how long is it going to be till you get to this amount. So after how many years? Let's call it X years. I'll get to $2. Whatever that is, that'll be our doubling time. So the easiest way to work these kind of problems is to use Excel. I'm going to pull up Excel to show you what I'm talking about. Hopefully you can see what we have there. So we started with $1. Now what I want to do is increase that dollar by 10%. So what I can do is in this spot here, I'm going to make a command. So I hit the equals key. When you hit equals, Excel knows you're ready to put a formula in. So what I wanted to do is I wanted to take the value in the cell A1 and multiply it by 1.1. Or increase its value by 10%. So what I can do then is I can type A1, and then you have to do a times, and you can do a parenthesis. So I want to take A1 and multiply it by 1 plus 0.10. That way it's growing at 10%. Enter. Here's the beautiful thing. I can go back to that cell, right? I can hit Control-C to copy it, and then get off the cell, and then I'm going to give myself so many lines here. So I'll go all the way down to 20. If I hit Control-V, watch what happens. It updates the formula to the next cell. So if you look at in spot 3 here, it's referencing A2, the one right above it. When I get to 4, it's referencing A3, the one right above it. So the formula actually updates. Well, now it's a trivial problem because I see that right in here, let me come back here with that thing. I can see right between years 8 and 9 is when it happened. So let me copy this. So somewhere between years 8 and 9 in here is when we had the doubling time. So the best that we can probably say is, I mean, you can probably make an estimate of about 8.5 years here, but it's definitely, by the time 9 years are over, it's definitely true. Now, this really makes it easy for you. Let's do another one. How long will it take an investment to double at an APR of 5%? So what I'll do is I'll go back to Excel and I'll just adjust my number so that instead of 10%, I change it to 5%. So I come back to Excel and I go back to the first instance of the formula and I see it was 1 plus 0.01. So I'm going to go and change that 0.1 to a 0.5 and see it updates it. Now if I hit Control C, it will copy this new cell, and I'll go and just paste it over top of the old ones. I went up to 20 last time. And here, it took quite a bit longer. Let me go ahead and grab this. So this time the doubling was between years 15 and 16. So there's our magic spot. Now there is a formula for estimation. This is called the Rule of 70. And it goes like this. If an investment is compounded at an APR of R%, then the doubling time is approximately 70 divided by R. So if we look at the last example there, the percentage was 5. So as our last example, in the last example, R was equal to 0.05, but that's not what you want. I'm going to erase that, in fact. What you want is the percentage, because you're going to make use of the 5. You're not going to make use of 0.05. So according to this estimate then, 70 divided by 5, that equals 14 years. Let's take a look at what we actually got. And ours was between 15 and 16. So you see, it is an estimate. It's just something I've seen salesmen use to give a quick estimate on how long a customer made me ask them, how long will it take me to become a millionaire? And they start doing computations like this. Now, on the other hand, we have something called half-life. This is the amount of time a decreasing quantity takes to become 1/2 its original value. And these half-lives, generally speaking, they're in regards to radioactive substances, but I've also seen it used for medicine. They often talk about the half-life of some sort of a medicine you're taking, and they go accordingly. After so many half-life times have gone by, apparently the medicine may not be effective anymore, and they may have to administer a new amount. Anyways, everything is almost exactly the same as before. So, suppose a radioactive substance decays at a rate of 10% per year. What is the half-life? Going into Excel and solving this is just as easy as before. Let me come back to it. Now, you can start with 1, but I'm going to change this to 100. It's just easier for me. And then basically, I'm going to want to see when it changes, at what time it takes for it to get to 50. So what I'm going to do here is now, instead of adding, well, let me come back to that cell. Click up in here. Instead of adding a percent to 1 inside of those parentheses, you would go 1 minus 0.10. That way you'd have 90 left after 1, what is it, year? Yeah, these are years each time it does that. And so I can do Control-C to copy that, come down here and paste it over those old numbers. And look, I'm looking for the place where it's halfway. And I can see it's between the 7 and the 8 right here. Somewhere in the 7th year, this thing decayed. Well, actually, I guess the 8th year. This is the 1st year. So during the 8th year, it became half. So the half-life is about 8 years. Let me go ahead and pull that. We don't have any methods to determine half-lives exactly because we don't use logarithms in this class. And so where am I looking? Right in here is the spot. So somewhere in year 8 was our half-life. And I can play the same game with 5%. So redo the last example. For 5%. And it's the same thing. I'll just go in Excel and I'll change the 10% to 5%. So I'll come back here and change the 0.1 to 0.05. And I'll copy that and then I'll paste it over. So now we see that it becomes half its value somewhere in the 15th year. So we can see the half-life is somewhere in here. So somewhere in the 15th year, the half-life. So at least 14 years. And we have an approximation for this as well. The approximation then goes like this. 70 over R, just like the other one. So half-life and doubling time work just the same way. So if I look at this last example, so the half-life so I would take 70 divided by 5, remember it's 5%, equals 14. And that's very close. Let's do it over here. That was a 10%. So 70 divided by 10 gives me 7 years. So the approximation is working very well for these things. Now for any of these, we're going to have formulas that look like this. where D equals the doubling time. And here, H equals half-life. So, if you're given the doubling time, you can work with this. Suppose an object doubles in size every 7 years. Then its size is 2 to the t divided by 7, where t is in years. By what factor has it grown after 13 years? So basically, we're going to put 2 to the 13 over 7. This would be the exact answer, but if you're allowed to do an approximation to it, let me grab the calculator. To get the calculator to do this thing, I think it's going to be a difficult thing here. We have 2, and I'm going to raise it. Raise it. I somehow have to get 13 divided by 7 in the exponent. And my guess is that a parenthesis is going to be the way to do it. So I'm going to start a parenthesis, 13 divided by 7, and I'm going to finish that parenthesis, and then I'm going to hit enter. So I was doing some of the homework problems, and I think 3 decimal places will be good enough. So I'm seeing 3.623. Similarly, suppose an object has a half-life of 12 years. What percentage of the object is left after 30 years? So here we just take 1/2, and I'm going to raise that to the 30th over 12. You might find it easier on your calculator to, instead of use the decimal, to go to instead of use the fraction, go to a decimal, and maybe even do the exponent as a decimal as well. I think the exponent is 2.5. So you could do this, although it wouldn't have worked on the previous problem because 7 wouldn't come out as such a nice clean number. But let me go ahead and work this. So I'm going to try to do 0.5, so 0.5, and then I'm going to raise this, and I need a parenthesis, so I've got to go parenthesis 30 divided by 12, and I end my parenthesis, and I hit enter. And if I go 3 decimal places, I have 0.17. Let's do this. 0.1768. 0.1768. And then with that, then we can say that only 17.68% was remaining after 30 years. So the same formula works for half-life as the other one. Here you have 1/2 to the t over h, where h is the given half-life.